Right, so next up is ionization energies. So ionization energy is just the energy required to remove an electron. So in this case, we're forming cations. So for example, if you've got your little atom here, what we can do is we can shoot energy at this atom. And when we shoot energy at this atom, and if we locate it or, shoot it at the electron, what we can do is we can pop out that electron. And so this is what's known as the ionization energy, or specifically the first ionization energy, or IE1, right? So how much energy to remove that first electron. So that's all we're going to take a look at here. Later on, we'll take a look at, removing more than one electron. So here's a table of ionization energies of some elements, and the bigger the number, the harder it is to remove the electrons. So we can see when we go from left to right, they're harder to remove. Right, generally as you go from left to right here, these numbers, they get bigger and bigger and bigger. And then the other way they get harder to remove is if you go from the bottom of the periodic table up to the top, right? So let's see if we can make sense of these trends. So when we're going to left to right, does it make sense that it's harder and harder to remove a proton? Let's think about lithium and fluorine. Lithium has 3 protons, fluorine has 9 protons. So we've got a little nuclei in the middle here. Our n equals 1 orbital, our n equals 2. They both have 2 electrons, right? That 1s2 electron. And then lithium just has a 2s1 electron, while fluorine has 2s2 and then 2p5. So we've got 7 out here. 1, 2, 3, 4, 5, 6, 7. So let's think about removing these electrons, and to remove these electrons, we have to get rid of their pool from that nucleus. So what we can think about here is our Z effective. What are these valence electrons feeling? And if we think about it for lithium here, we've got 3 protons. We've got 2 core electrons, so 2 shielding. So each electron feels a pool of +1. The Z effective for fluorine, meanwhile, right, again, here we have 9 protons this time. We still only have 2 shielding electrons, so they feel a +7 pool, right? So it makes sense that it would be much harder to remove an electron from fluorine than it would from lithium, right? So that left to right trend makes total sense. What about the down to up trend? Let's think about lithium again, and in this case now we'll talk about sodium, right? So we've got lithium and sodium right here, and we can see it's easier to remove an electron from sodium than it is from lithium. So if we think about our structure of lithium, we have that n equals 1, and then n equals 2 orbital, and then we've got 2 electrons here, and then 1 on the out here. Whereas in sodium, we have our n equals 1 with its 2 electrons. We have n equals 2. In this case, this is totally filled as well, so we've got 8 here. And then our n equals 3 is where we have our lone electron. And so in this case, this lone electron is significantly further from the nucleus. And since it's further away, it feels less of a pull from that nucleus. So it's easier to remove. And so overall, this trend as well, it makes sense, right? All of this stuff is predictable. And by using our Bohr model, we're able to predict, what these ionization energies kind of really are. Of course, with science, there's always going to be exceptions to any rule. There's really no rules. They're all just kind of guidelines. So one exception we have here is taking a look at group 2 to group 3, right? We see that this is an exception. We expect the number to grow when we go from left to right, but in this case, it actually shrinks, right? It goes from 9 to 800, right? That number went smaller. So what's going on here? And can we explain away this exception? And the answer is yes, we can explain away this exception. However, the Bohr model is not going to be good enough. So let's think about our beryllium and our boron. And what we want to think about now is our quantum mechanical model, in which case we have these orbitals. If we think about the beryllium, we have the 1s orbital with its 2 electrons, the 2s orbital with its 2 electrons, and then the 2p orbital, which is higher in energy than the 2s orbital, but it's unfilled for beryllium. And then we have the 1s orbital for boron, the 2s orbital for boron, and then in the 2p orbital, we now have an electron up here. So this electron is higher in energy, and so it's easier to remove. It's in a higher energy subshell, so it's easier to remove. If you're wondering why the 2p and the 2s are in different energy levels, that's to do with what's known as penetration, which I forgot to mention earlier, so maybe I'll make another video of it. So maybe if you're in the future, you're already know about penetration. If not, just see your textbook. It's not that important of a topic, but it explains why our 2s and our 2p orbitals are not in the same energy range. And generally, the higher something is in energy, the less stable it is, the easier it is to remove. So even though we've got an exception to our trend, with the power of quantum mechanics, it should make sense. Let's see if we can spot out any more trends. And obviously, since I've said that, we're definitely going to find some more trends or more exceptions to the trends. And that other exception is right here. Going from group 5 to group 6, we can see going from nitrogen to oxygen or phosphorus to sulfur. Again, our ionization energies are lower instead of bigger. So can we explain what's going on? And the answer is yes, we can. So if we think about what's going on with nitrogen versus oxygen, in nitrogen, we have that 2s orbital, and it's got a pair of electrons. And then our 2p orbital, all of these electrons are by themselves. Whereas in oxygen, we have the 2s orbital with its 2 electrons. And then we have the 2p orbital has 1, 2, 3, 4 electrons. So what we can see here is in the oxygen, what we had to do is we had to start pairing the electrons. So we've got electrons in the same orbital. And electrons repel one another, right? They're the same charge. So there's electron-electron repulsion. And so they don't want to be in the same orbital as much as you may think. And since they're repelling one another, they're easier to remove. Right, so these ionization energies, right, were experimentally found. Somebody did some experiments, found these ionization energies, and what they found is that with quantum mechanics, it totally makes sense.